There we go. It's important to realize that the balanced equation lets you use any two chemicals in the equation, lets you compare them. So it's fine. The previous question had octane and I think water, was it? Or maybe CO2? Yeah, it was water. So we were asking you start with a certain amount of octane, how much water do you make? That's fine. You could also start with a certain amount of octane and ask how much CO2 do you make? Or this question is saying we start with the amount of octane, how much oxygen is needed to react with that? So in our pizza analogy, this would be instead of how many pizzas am I going to make, it's I have this many crusts, how much cheese do I need? Okay, so you're comparing the ingredients rather than asking about how much stuff are you going to make. Okay, the other way you could also do it is sometimes you'll say, I made a certain amount of product. How much reactant did I use? So like I made 3 pizzas. How much cheese did I use to make those 3 pizzas? So you can compare any two chemicals. Doesn't matter. And half the time, like I would almost just say, just do the problem and then try to figure out what it means if you need to figure out what it means. Because eventually, when you do enough of these, you'll start to actually read the words and try to understand what it means. But you don't have to understand what it means to get the problem right. I know that sounds like a really bad teacher way of describing things, but you don't. You can do the problem without actually understanding what you're doing. Okay, so highlighting what we're actually looking at. 22 moles of C8H18. That's what we're starting with. Okay, so I know I'm going to have that as my starting point, 22.0 moles C8H18. I made my cursor too big. Okay, then I'm going to moles of O2. Why? Because that's the only other unit. It's a number with a unit, and then it's a unit by itself. Those are my only choices of where to start and where to end. And just like I've done a bunch of times already, this unit goes on the bottom so that it cancels out. This unit goes on the top so that I stay with that, so that I know that that's what I'm going to have. And then I ask myself, do I know a conversion factor that gets me from moles of C8H18 to moles of O2? And in a second, I'm going to reiterate those potential conversion factors that we've assembled up to this point. But this is the new one that we're adding in. Moles of one thing to moles of another. And the numbers come from the balanced equation. So moles O2, I just pick up the coefficient there, 25. Moles C8H18, 2. So it's like first you need to know, is this a valid conversion factor? Like, do we know how to, use this? And then where do I get those numbers from? And we're going to make that list again today. Okay, so 2 and 25. It's 275 moles of O2. Okay, so what is it saying? It's saying that if I have 22 moles of octane, the C8H18, I need 275 moles of O2 in order for them to react completely. Just like with the pizza, it would be like for every 1 pizza, I need 2 cups of cheese. So if I want to make 10 pizzas, I better have 20 cups of cheese. If I want to react 22 moles, I better have 275 moles of oxygen. Okay, that's the correct ratio for the recipe. So also, did you see how I did that? I got the right answer without actually understanding it, and then I explained it to you guys what it actually meant. That's fine. Do the problem, figure out what the right numerical answer is, and then worry about what it actually means. There's no problem with that. It might actually be easier that way. Okay, let's do one more, just like a concept question, and then we'll kind of talk through the conversion factors and add to how do these problems get more complicated. Okay, so just take a look at this for a minute. The purple dots, those are supposed to represent sodium. And then these are the oxygen molecules. So 3 little O2 molecules. Okay, so you don't actually have to do math for this, but I want to show you what the math would be. Now, we're not talking in moles at this point. We're actually talking about molecules and atoms, since we're looking at a picture, scaled down. So if I have 3 O2s, what they're asking is how many sodiums do I need to react with it? Okay, so this is again comparing the ingredients in the recipe. So normally I need 4 sodiums for every 1 O2. So that just means that if I have 3 of them, I need 3 times that, or 12. So it should be C. And if you want to see math-wise how I did that, it would be 3 molecules of O2 is what I'm starting with. How many atoms of sodium do I need? But I'm still getting the ratio from the balanced equation. So 4 sodiums for every 1 oxygen. So that's why I know I need 12 sodium atoms. It's always good when we have pictures because then you can actually push the math to understanding the concept. Okay, so all the problems we've done up until this point are just in terms of moles, or in this case, atoms and molecules. We don't usually measure things out in moles though. It's not like you go into a laboratory and you have a balance that you put stuff on and it says that's this many moles, that's this many moles. No, you have to do a conversion. It weighs out grams and then you have to convert it to moles. So the rest of the problems are going to be incorporating other ways that we measure some compound, either that goes into the reaction or that comes out, and it's not necessarily going to be in moles. Okay, the thing that's going to stay constant is this mole to mole conversion that we've now introduced. So in order to prepare for that, let's go write a list of conversion factors. And I'm going to try to, we've done this a few times, but I'm going to try to make this one as generic as possible. So not be like, exactly the numbers that you would put in, but where to find them. Okay, so we'll say conversion factor units. So just like this over that. I might give an example for some of these and then where to get the number. You guys know that means number, right? Not hashtag. I remember when that first started, my life is based on how old my kids are, or this is before I had kids, so it was like what job I was in. So it would have been early 2010s. Hashtag blah, blah, blah. I'm like, what does that mean? I literally had to everything I learn about pop culture is from my students saying things, or now my children saying things. If I hear 6'7" one more time, I'm going to freaking lose my mind. It's one thing if I say something I don't know, it was 6 or 7, and they're like, 6, 7. But when they just randomly go around and they're like, 6, 7, that doesn't have, why did you say that? I'm going to lose it. Okay. At least they're not saying, what was the other thing? Skibbity? At least they're not saying that anymore. Okay, that's not a hashtag, that means number. This is why we got on this topic. Okay, One of the first conversion factors we did were like metric conversions or English to metric, okay? So we'll put metric and English. So for example, this could be centimeters and inches, or maybe kilograms and pounds. Where do you get that number? That's the exam equation sheet. We also did metric to metric conversions. So this would be maybe grams to milligrams or meters to nanometers. And those ones you were supposed to memorize the prefixes. If you don't know how to do that, like use those memorized things, it's time to learn. The other thing we did in chapter 1 was density, so grams per milliliter. Now, because we're starting to get into balanced equations where we have multiple chemicals involved, I'm going to abbreviate this as like X and Y. So for this one, I'm going to say grams of X, milliliters of X, meaning like they have to be the same thing. So density would be measured in grams of water per milliliter of water. Okay. When we're doing a balanced equation, it's like moles of one thing to moles of another. So I'll say moles of X to moles of Y, just to emphasize the point that is it the same thing or is it two different things? Okay, so that's density. So that might be something you look up in a table. It might be given in the problem. Very often it's just given in the problem and it throws people off because they're like, wait, do I start with that number? If you have something that has a unit over another unit, they want you to use it as a conversion factor in the problem. You're not starting there. You're going to use it to get to your answer. Okay, so that was chapter 1. Chapter 2, we started talking about masses, and this is chapter 2 and 3, because we talked about masses of atoms and elements. Then we started talking about it with molecules. So we had, and this one is not, I want to de-emphasize this one because we hardly ever use it, but AMU per atom or AMU per molecule. And this would be of the same thing. So like AMU of carbon per one atom of carbon, or AMU of water per one molecule of water. And that's from the periodic table. So if it's just carbon, oh, did you guys see we have a periodic table now? It's a little bit funny. I'm really glad that this didn't go up until after your first exam. So if I teach in this room next fall, I'm going to be up a creek, because there's like the element names and stuff are up there. Oh well, it's just so that I can reference it really quick and be like, over here, over there, see carbon, whatever. So the periodic table is where you're going to go if you want to get the mass, either for AMU per atom or for a molecule, or for the thing we're going to use it for more, which is a mole of atoms or a mole of molecules. So that's our next thing. Grams of something per one mole of that thing. Also the periodic table. So this could be grams of carbon for a mole of carbon, or it could be grams of carbon dioxide. If it's a molecule, you just have to add them up from the periodic table. All right. So I'm trying to de-emphasize this one because we're not going to use it a ton by circling it. That's the opposite of de-emphasizing it, but just don't worry so much because we're not going to use that really frequently. The other thing we're not going to use really frequently is converting between atoms or molecules and moles. We're going to mostly work in moles from now on, but you do still need to know it. So 6.022 times 10 to the 23rd atoms or molecules per mole. So that one's like, you don't have to look for the number anywhere. It's just always Avogadro's number. Of course, I run out of space. Let me try to shift this up a little bit. Okay, and then the last one that we just introduced is moles of one thing, so moles of X to moles of Y, and that's from the balanced equation. Okay, so the reason why we're reviewing this is because we're going to keep using the moles of X to moles of Y conversion, but we're going to add stuff on the other sides. Primarily, we're just going to be doing grams to moles and moles to grams conversions mixed in there. Okay, so that's our goal today, is to do lots of practice where we don't just convert with a balanced equation from moles of one thing to moles of another, but maybe we first get from grams to moles and then do a mole to mole conversion. Then maybe we convert from that moles out to grams again. I should be turning around if I want to do this left or right. Okay, so let's look at a couple examples. Wait. Is that the one I want? Yes, I guess it is. That is not the one I started with. Which one did I start with in my other class? Is there one? Oh, yes, thank you. Okay. The world burned, okay, obviously I need to update these example problems. The world burned the equivalent of 3.7 times 10 to the 15th grams of octane. So this is the one we were looking at before, C8H18. And I'm just going to rewrite the balanced equation so that we have it handy. So it was 2 plus 25 O2, making 16 CO2 and 18 H2O. Okay, so this is octane, C8H18. Oct, like 8, that's where it comes from. How many grams of CO2 were produced? So we're starting with grams of octane, looking for grams of CO2. So if you initially start this problem, you might say, like, start by trying to convert. And it's fine if you do this because it's nice for you to have the same approach every time. If you see immediately that this isn't going to work, that's fine. But let's pretend that you don't see what you're going to do here, and you just start to do this like you've done every other problem. And you say the number and the unit that I'm starting with, the unit of the thing I'm trying to get to, and then you try to set up a conversion factor, and you put the unit down here to cancel out, and the unit up here to get to it. And then you pause and you say, do I know a conversion factor that gets me from grams of CO2 to grams of C8H18? No. Go back to this list. Have we ever compared grams to grams? There was actually one time. I feel like I just want to take that out of the unit because it's confusing. But ignore that time if you know what I'm talking about. We don't ever compare grams of one thing to grams of another to use a balanced chemical equation. It's just not one on our list, okay? Because that's not how things react. They don't react like 10 grams of this to every 1 gram of that. They react by their atoms hitting each other and rearranging. So it's not appropriate to talk about them in terms of their mass and what their mass ratios are. The balanced equation tells us what their atom or molecule ratios are. And we can scale that up in terms of moles but we would never think of these ratios here as having to do with grams, okay? So this is not gonna work. So at that point, if you started the calculation like this, now you've realized that's not gonna work. So what we need to do is plan out a unit route to help us understand how can we get from grams of that to grams of this. Because what it's really saying is we need to go through multiple steps. We can't do it in just one step, okay? So I'm gonna start the unit route with the grams of octane here. So grams of octane. And I'm gonna have to convert to something so that I can eventually get to grams of CO2. And here is the big secret of chemistry calculations. You're gonna be converting to moles most of the time, okay? So because the balanced equation is the ratios are in terms of moles, almost every time, whatever you start with, you're gonna convert it to moles of that thing. Now, sometimes the problem might start with moles, like in the one above. This started with 22 moles. Okay, well, we don't have to convert in that case, but here we're given it in terms of grams. We need to convert that to moles. Okay, so I'm gonna convert grams of C8H18 first to moles. This is where it becomes really important to not just write moles, but write moles of C8H18. Because we're trying to get to grams of CO2. Do we know a conversion that gets us from moles of C8H18 to grams of CO2? No. We can do moles to grams if they're the same compound, but we cannot. The only way to get between two different compounds is a mole to mole conversion. So we need to first go to moles of CO2. Sorry, I'll fix that. I'm just trying to move this over and give myself some more space. Then we can go to grams of CO2. Okay? So this is the part that is going to happen all the time in these problems. You're always going to have moles of X to moles of Y. You're going to do this conversion that's what defines a stoichiometry problem. That's what makes it stoichiometry, is that you're using the ratios to convert from moles of one thing to moles of another. Sometimes you might already start with moles, and that's great. But if you don't, you're going to have to do a conversion that gets you to moles. And if the answer wants it in something different other than moles, in this case grams, then you're going to have to convert out of grams. So I had somebody at the end of last class who was like, I'm just having a hard time figuring out that unit route. Once I get there, then I can do the calculation. These three steps, this is the one that will always be there. The other two are if you need them. So this is always part of a stoichiometry problem, mole to mole. The gram part only comes in if you need it, if you're not already in moles. And the mole to gram part, that comes in if you need it, if the answer wants it in grams. If it wants it in moles, great, you just end there. Okay? And looking forward into chapters 5 and 6 and so forth, sometimes we're going to have other ways of measuring stuff, like would I measure water in grams? No, not usually. Usually you're going to measure water, it's a liquid, right? You're going to pour it out. So maybe I measure it in milliliters, and then I have to convert that to moles. Okay? So there are going to be other ways that we get to moles. In fact, I think I have this little image that I used as like a, I don't know, like an overview during finals. That's like all these different ways that we can get to moles so that we can then do a mole to mole conversion. And then all these different ways that we can get out of moles to get to some value that we want, okay? So you need to remember that this is the thing that is going to be a constant part of these calculations. And then if you need them, you have the others. Okay, I'm also gonna do this as 3 separate calculations. Since this one will incorporate all 3, I'm gonna do it as 3 separate calculations, and then we'll put them together. So you'll see pretty quickly like how you can put them together to make it go faster, but I want to show you at first all the steps, okay? Before I do that, I'm going to erase this. So if anybody wants to take a picture, I do not post these notes because I end up erasing things and rewriting them, and it's just a mess. So I don't post them for that reason, but if you guys want to take pictures, I don't care. So last chance. Okay. All right. So I'm going to try to color code these 3 steps so that we're clear on what's happening. All right, so step 1 is the grams octane to moles octane. So I'm going to write this just as a single step, grams of octane, and then I'm going to go to moles of octane, C8H18. So like I've done every other time, grams goes on bottom, moles goes on top. That works because it's grams of one thing and moles of the other. And then you say, where do I get that? Grams and moles. The moles is 1. The grams comes from the periodic table. So just wake yourself up a little bit. Everybody go calculate the molar mass of C8H18 so that we can put that number in there. So this is 12.01 for carbon times 8 plus 1.008 for hydrogen. This is looking to see if the sig figs are similar. They're slightly different up there. Times 18 for hydrogen. So 114.224 grams of octane per mole. Now, this is an enormous number because we're talking about gasoline burned by the entire world. So, okay, so this is, and this brings up an interesting point too. I would never, you don't want to round too much if you're separating them out because this isn't the end answer, right? This is moles of octane. We're looking for grams of CO2. This is just part 1. So usually what I do is just add an additional significant figure. So I'm going to call this 3.24 times 10 to the 13th rather than just 3.2. If it was the end answer and I wanted 2 sig figs, I would drop it there. But like if you round too early, you might get what we call a rounding error. So it might come out slightly different because you rounded too early on. Okay, so that is the part that I blocked out here in blue, okay? Now we're gonna do the second part, which is moles of C8H18 to moles of CO2. So I'm just gonna take this number and start another calculation. 3.24 times 10 to the 13th moles C8H18. We're looking for moles of CO2. And then we just do the same thing. This unit goes on the bottom, that unit goes on the top. Moles C8H18, moles CO2. And then I ask myself, do I know a conversion factor that gets me from moles of CO2 to moles of C8H18? Yep, 2 different compounds. They're part of the chemical equation. We go to the balanced chemical equation for that. So 16 for the CO2 and 2 for the CH18. So hopefully you're starting to see that just like the other problems we did, there are like conversion factors that get used over and over again. You just need to be able to identify that it is like a valid conversion factor, one that we know how to get in between, and then where to get the numbers from. Okay, so now that value, oh, I hate when my calculator doesn't give it to me in the correct, like in scientific notation. 2.59 times 10 to the 14th moles of CO2. And then the last part is we need to go from moles to grams. So again, I'm going to take that number down here and start a new calculation. And I'm trying to get to grams of CO2. So moles of CO2 on bottom, grams of CO2 on top. And then it's almost like the same thing as the first one, just in reverse. Now I'm going from moles to grams, not grams to moles. So the moles is always 1, and the grams comes from the periodic table. For CO2, that's 44.01. So my final answer is 1.1 times 10 to the 16th grams of CO2. Okay, so while you guys are like catching up to where I am, I'm gonna copy and paste and show you like color-coded how you can do this as one calculation, because just to save yourself time and energy, you're probably going to want to do that. Okay. Okay, so there's my first conversion factor. I feel like I'm going to have to squeeze to get all of these in there. And the second one, here, it's the purple one. So I'm just combining all of these together. I'm writing them as a single problem, because that's what you're going to end up wanting to do most of the time. Now, don't think that because I'm saying it's okay to combine them, that eventually you're going to be fine to just do them in your head or something, okay? If I'm writing an exam and I'm writing the answer key and I want it to, you know, be right because I have to run it through the Scantron and I don't want to have to do it twice, I'm actually going to write out all of these conversion factors. Okay, and I've been doing this, I realized this in my other class that I was like, I've been doing this for 20 years, because like for a while there, I just said 20 years. And then it struck me that like this spring is, okay, I guess I can still say, if I can round down, I can still say 20 for like another year. Next fall though, will be 25 years from when I was a freshman in college. So I'll probably have to start saying I've been doing this for 25 years. We'll just ignore high school and pretend like that doesn't count. Because it doesn't. Okay, so if I wanted to perform this calculation as 3 steps all together, I just need to verify that everything cancels out. So grams cancels out with grams of CH18, moles CH18 cancels out with moles of that. Moles CO2 cancels out with moles CO2, and you're just left with grams of CO2. So this will give you the exact same answer. It's just performing the calculation all in one step. So each of those like blue, purple, and green steps, you're looking at the conversion factor that corresponds to each of those. You do still need to write it out, though. If I have to write it out after 20 years, then you have to write it out for the rest of the year you're with me, okay? If you're going to be in Chem 2. Certainly if you're on an exam. Don't try to think you can just think through the conversion in your head. Okay, so what we want to do for the rest of class, 2 more problems probably, is we want to do some examples where we don't necessarily have to do all 3 steps. So we've done ones where it was just the middle step, and now we've done ones with both of the other steps, and now I want you to practice having to actually like write out your own unit route and decide, do I need like 2 of the steps? Do I need all 3? Do I just need 1 of them? So I think what we'll do is, let me pick. I'm either going to do these 2 or the next 3. Grams, moles to grams, moles to... Okay, let's skip those. Let's do this one, and we'll do all 3 parts, okay? So it's going to be this same chemical equation for all 3 parts, but there's 3 different questions. This one and then 2 on this, okay? So let's have you work the first part here. Then we'll talk about that. Then I'll let you do the last 2 and check answers. So I'm going to give you, a minute or 2 to work through this on your own to start. In case you're not up to date on your naming, that's potassium chlorate. Chlorate's a polyatomic ion. The other one is potassium chloride because it's an element, ends in "ide." Okay, so this one was just the middle part, just the mole to mole conversion. Moles of one thing to moles of the other. You can probably identify that pretty quickly when you just see in the question moles of something, moles of another. Okay, it's just that middle part. Let's give the next one a try. So same equation, just scroll up or, in your notes. And feel free to work both of these if you want, if you have time. Okay, so I'll give a couple hints up here. Just don't look if you're doing good. Okay, so before I go and actually put in the conversion factors, let's just talk through and make sure you, because like this part I feel like is probably the easier part. So the hardest is probably going to be figuring out the unit route. What steps do I need to take? So in this one, you are going from moles of one thing to grams of a different thing. And this one, you're going from grams of one thing to moles of a different thing. So they both end up having to have two steps. Again, the middle step you always end up needing. You need the moles to moles. You need the moles to moles. It's just, is there anything else? Okay? So in this one, moles to moles and then to grams. Here you have to get into moles before you do that. So I'll go ahead and put the values in and then do the answers so you guys can check those. So O2 is 3 and 2. And this one I think is just 2 and 2, right? Yeah. And then when you do grams to moles, that mole value is always 1. And the grams is whatever is on the periodic table. And then I just plug it in. So this one is 120 grams of O2. And this one is 4.28 moles of KClO3. Did I get that molar mass of KCl right? 70, okay, yeah, looks good. Okay, so Friday, we'll do a little bit more of this before we add on kind of the last idea, and then we'll practice that all day on Monday. Okay, like the red ones? Yeah. So anytime you have moles and moles together, those come from the balance number equation. So if I just scroll back up, that's those numbers that are in front there. So like moles and moles, this one is O2, so I just look, right there. This one is that, 2 there. So that's for if it's moles of one thing and moles of another. If it's grams and moles, the moles is always 1 and the grams is 3. So O2, you look up what oxygen is, 16 times 2, so 32. Same thing on this one. You look up what potassium is, add it to whatever chlorine is, and get that. And then right now, that's the only one you've been doing in this chapter so far. And in fact, we'll have a lot of others in there. It's not like you have to build up those grams or anything. Good? Yeah. Okay. Yes. Okay. Probably. I don't actually know, but that seems like if it's not who you need to inform, then they would certainly know who to tell you to tell. But I'm pretty sure you're right too. Yeah. Yep. Yeah. So each oxygen is 16 on the periodic table, but there's 2 other ones. So you just have to do times 2. It's just like if you do KCl, you look up what K is, you look up what Cl is, and you add them together. This one, it's like you're adding 2 oxygens.
So we use the formula that was
No.
Okay.
So that one is
like that one. So because when I was doing it, I
did it
time
times 3.
Yeah.
Okay. Yes. Just the formula of this.
Okay.
The 3 is only what you use in
For
these
the,
ones.
okay. For the
Yep.
wolves.
Mhm.
Okay.
Yep.
Thank
Good.
you.